And this is where we were last time, where we were describing how to make limonene from this linear precursor. We had identified the two isoprene units. We had identified the bond between gold 5 and red 1 as the bond that's present in the linear precursor. We talked about how the leaving group's got to leave and then come back on the tertiary carbon, so you can rotate around this bond, positioning red 5 in the right place. Then the leaving group comes off again. You get a resonance stabilized carbocation that's on both red 2 and red 5. Then the pi bond between gold 2 and 4 attacks red 5, and you make the new blue bond that's not present in the linear precursor. And then to get to limonene, all you need to do is that elimination step. Okay, so you're seeing put together some of the basic steps of terpene chemistry that we've talked about. I want to show you how this pathway can lead to lots of different and interesting intermediates or interesting products. For example, from this same pathway, in fact, from this common intermediate, you can get a couple of weird and interesting products. So let me draw a couple of them. One of them looks like this. And this one's kind of challenging to draw. You have a carbon here that has two methyl groups on it, and it is bonded to both this carbon, and they're both dashes instead of wedges. So you have to think about this six-membered ring and then this carbon below the six-membered ring bonded to those two carbons. If you wanted to draw this in something that resembled a chair, I suppose you could. It would probably look like this. With that carbon below the ring. And believe it or not, you can get here from here without very much trouble at all. Though, as you look at it, it probably looks like, what the heck are we doing? This product is called alpha pinene, and it is a component of pine oil from pine trees, okay? So it has that origin. Let's see if you can look at, where'd the other methyl group go? Let's see if you can look at this structure and, doing what we did last time, pick out the isoprene units. So again, we start with the dimethyl tail. So that's going to be this one. So that's automatically got to be carbons. This one's got to be gold 3, 1, and, oops, I'm wrong. Gold 2, 1, and then 3. Then you can identify the other isoprene unit with the branching methyl group. Okay. And now, sort of by analogy to what we did above, we could let this one be gold 4, this one be gold 5. That would make this red 1, this, except I need to switch colors, don't I? 1, 2, 3, 4, and 5. So if we compare what we've done in this alpha pinene product relative to where we were with that purple highlighted common intermediate, this bond between gold 5 and 1 would have been present in the linear precursor, and we already made this bond between gold 5 and gold 4 and red 5, right? So what's the new bond? What is the new thing that we've got to explain in alpha pinene that wasn't present in that carbocation precursor? Go ahead.
Is it the bond between red 4 and gold 2?
Yep, has to be that one. The bond between red 4 and gold 2, because that's the only thing unexplained. That's the only bond that we have here that was not in the purple intermediate. Okay, good. So now we know that's the new bond we have to make. Can you explain that bond using one of the steps that we learned about, which are leaving group leaves, nucleophile attacks a carbocation, and base eliminates a beta proton. So let me copy this structure and erase the arrows from the base removes a proton step. And the question will be, is there anything you can think of that might make a new bond between red 4 and gold 2? That was not rhetorical. Yes, go ahead.
The double bond to the top could attack.
All right, so let's have the double bond from the top, which again, if you remember what a pi bond is, you've got electron density above the plane of the page and below the plane of the page. So let's have the electron density below the plane of the page reach back, reach under, and attack the carbocation on carbon 2, which would look like that. Okay? Good. Now, does that approach, does that reaction explain why the bond ends up between 4 and 2? Why does the new bond with gold 2 go with red 4 instead of red 2? Yeah. Right, you want the more substituted carbocation. So you're going to use that Markovnikov rule to get you there. So let's just draw, and sometimes with terpene chemistry, it's useful to draw things in a weird sort of, with weird, really long bonds, just so you can get the connectivity right, and then after you do that, you can redraw things with more realistic bonds. So I'm going to relabel our carbons 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. What you just proposed is a new bond formed between 4 and 2 with a positive formal charge on carbon 2. So what we need to add then is the new bond between 4 and 2. All right, now that looks ugly, but it at least establishes the connectivity, and then if I want, I can redraw it in a slightly better way, which would be like this. I won't keep numbering the carbons here other than to show us the labels. Here's the bond that was present in the linear precursor. Here's the one we made before. And then here is the one we just barely made. Okay, good. So do you see how we made that connection? The product increased in complexity dramatically by making that one carbon-carbon bond. It went from something that we were okay looking at to something we were like, whoa, what just happened there? But it's from that same carbocation. So one question you might ask is, how do orange peels know to make this one? And how do pine trees know to make this one? And the answer is, I don't know, but it has to do with the enzymes that are expressed in orange peels versus pine trees. Okay, we're still not to the alpha-pinene product. Can you think of a mechanistic step that allows me to get from this carbocation to this product? Base eliminates a beta proton, right. So you look for protons that are beta to the leaving group. Here's one. And here's one. To get alpha-pinene, the base from the enzyme removes the proton, and we do an E1 style elimination step, and that gets us to the product. If we eliminate the other beta proton, you can get a related product, which is called beta-pinene, which is just an isomer where the pi bond is in a slightly different place. Okay? So you're starting to see how nature can generate very different products from simpler starting materials. Go ahead.
So maybe I'm just rusty on OChem 1, but I thought the proton on red 4 would be abstracted because it's
Okay.
more substituted.
Right, so you're pointing out there's still a proton on red 4.
Or is that just enzyme selectivity that makes that happen?
So it's actually not likely enzyme selectivity, it's fundamental structure. And I will tell you this, in order for the protons that are beta to the positive charge to be able to be removed, they have to be hyperconjugating with the empty p orbital on this carbon, meaning they have to line up with it. From our perspective, the p orbital is coming out of the page. I could draw it for you, maybe we should. It's too much, well, I'll do it and then I'll erase it because I won't like it. But here's the p orbital. I'm running out of like colors that I haven't used. So this lobe is, oh, no. So it's about end of semester evaluation time. So now is the time when you want to tell BYU how much time I waste on coloring. Here is the upper lobe of the p orbital, the lower lobe of the p orbital that's below the plane of the page. This proton, whether it's a wedge or a dash, can line up with that empty p orbital. This proton can too, simply by rotation around the bond between the methyl group. If you look at this proton, it's at the linkage between 3 carbons. If you built a model, you would see that this proton is going to be held perpendicular to that p orbital. So it can't really hyperconjugate with it, which means it's not going to be acidic enough to be removed. And the other explanation is a double bond here. If you imagine this double bond isn't there and try to put it there, the geometry isn't going to work great for this 4-membered ring fused to a 6-membered ring connection. So it's a little subtle, you don't see it on paper. If you built a model, it would become clearer, but that's why. All right, good, what else? Yeah?
Would we also get a product where instead of dashed lines, we have a wedge?
Right, would you also get a product where you have wedges instead of dashed lines? Yeah. Yes, if you were doing this in the lab. One thing I didn't point out, but is clear from the limonene product over here is you get the dash, and that stereochemistry is set in this step where the pi bond between gold 2 and 4 attacks red 5. I didn't show it here, but it is. And the thing that controls that is likely the enzyme. So the enzyme is chiral, and that means that the chiral catalyst can favor one enantiomer over the other. But yeah, otherwise you would not be surprised to see the wedge product. Okay, good. Others? Okay. So you've seen some terpene products. I'm going to show you another one that's available from this same starting material. And this is going to allow us to introduce the 4th reaction toolbox that's useful in terpenes. So we're going to draw now, why not? This one, I like this one. So you're going to like this. This comes from that same carbocation precursor. So I'm just going to copy it and put it here. So this is called alpha-thugine, and it is, I think, found in rosemary oil. I like it because it looks like a duck. I didn't know whether you guys were raised with that or not. I think that was early 2010s, so maybe you were 3 at the time. I don't know. No. It was even before 2010s. It was like late 2000s, 2008. So okay, I'm not good at math on the fly. Okay, you probably would have been 5 or 6 or something when that came out. Okay. Well, anyway, so you've got memories of this. Put it on my bill, right? Okay, so let's see, looking at alpha-thugene, how we can get, let's see what the connectivity is. And again, we're going to start by identifying isoprene units. This should be getting a little bit easier by now. You should see this is the dimethyl tail. That's carbons orange 1, 2, and 3. That would make this 4. This is 5. 1, 2, 3, 4, and 5. So we'll highlight in red that isoprene unit and in orange this isoprene unit. Just following along to what we've done before, this bond between red 1 and gold 5 was present in the linear precursor. The bond between gold 4 and... What happened? Huh?
Oh, I think he's just drawing red and purple over the ball.
Sorry. Yep. I thought the screen had gone dead. Yeah, so I'm drawing in the red ink the bond between 5 and 1 that was present in the linear precursor. And then in blue ink, the bond between gold 4 and red 5 that we made in this carbocation. So, which is the new bond that we have to explain here? Which is the new bond in alpha-thugene that's not present in that carbocation precursor? Between red 4 and gold 4. Okay? So we got to explain that one. Now, looking at the starting material, we do have a nucleophile on red 4, that pi bond. And we just barely used that in making alpha-pinene, attacking the carbocation at 2 to make a new connection that would leave a positive charge on carbon 2. What's the problem here? If I wanted to make this bond by having this pi bond attack a carbocation, why can't I make it right now with carbon 4, with gold 4? Go ahead.
You do a hydrogen shift?
Good, right, because the carbocation is not in the right place, right? The connectivity means I need an electrophile at carbon 4. Right now the carbocation is not in the right place. So one solution is the thing you hate, which is carbocation rearrangement. Right, so step 4 in our toolbox is carbocation rearrangement. And this can either be a 1,2 hydride shift or a 1,2 methyl shift. And you will also see sometimes 1,2 alkyl shifts. But all of these just involve, and let me just illustrate carbocation rearrangement one last time so you have an idea of what's going on. Carbocation rearrangement can happen when you have a p orbital with a positive charge on the associated carbon adjacent to either a carbon-hydrogen or a carbon-carbon bond. In 351, you were taught to worry about carbocation rearrangement when you had a secondary carbocation adjacent to a tertiary carbon. And when that happened, a 1,2 hydride shift would generate a more stable tertiary carbocation. That's when you were taught to predict that this would happen. And that was going to limit you from all sorts of uncomfortable weirdness about predicting products. Well, nature is not so constrained. So nature allows carbocation rearrangements as long as they lead to more stable products ultimately. So in terpenes, you will often see carbocation rearrangements that shift one tertiary carbocation into another. And it's fine because they're of similar stability. So what happens in a carbocation rearrangement, this CH bond here is already hyperconjugating, donating electron density to the adjacent p orbital. It literally just leans over to the left and then dumps its electron density into the empty p orbital, leaving a carbocation where it once was, and then the new CH bond is over here. And you can see how this would lead from one tertiary carbocation to another, so you'd expect the equilibrium constant to be pretty close to 1, meaning it's a reasonable mechanistic step if nature needs to access a product. Now, I'm still not going to ask you to predict that a carbocation rearrangement like this would happen. You've learned in 351 you predict it when a secondary carbon is adjacent to a tertiary or quaternary carbon such that a 1,2 shift of either a hydride or a methyl group or an alkyl group would give you a more stable tertiary carbocation. Here, though, if you have a result like we do with alpha-thugene, and you're like, a nucleophile must have attacked carbon-4, but carbon-4 is not an electrophile, then you propose a 1,2 hydride shift that would allow what you know has happened to happen. Does that make sense? Okay. So what's going on here then is a 1,2 hydride shift. Whereby the proton on gold 4 leans over and then makes a new bond with gold 2. The rearranged carbocation is going to look like this. We now have a positive charge on gold 4. And now we're perfectly set up for the pi bond between red 2 and red 4 to attack the positive charge on gold 4. All right, so I'm going to just number atoms again real quickly. Right, and so now here is the attack of the pi bond. That's going to make the new bond. And let's just, sometimes as I said, it's easiest to redraw the molecule, to draw the molecule with a weird looking bond so you can at least get the right connectivity, and then you can revise it afterwards to make it look prettier. So I'll maybe drop the numbers, but just continue to highlight the isoprene units. Again, the new bond is going to be between red 4 and gold 4 so that the positive charge can be on the more substituted carbon. Now, checking what we did here with what our product is here, our product has a 5-membered ring containing red 1, 2, 4 and gold 4 and 5. 1, 2, 4, and then gold 4 and 5. And then it has a 3-membered ring that contains red 4, red 5, and gold 4, and that's what we've got here. And if you want to redraw this in a way that makes it seem less strange, there you go. Lastly, what do we do to get alpha-thugene? What's the last step we do? Yeah, base removes proton adjacent to positive charge. And there we go. Okay, those are the toolboxes for terpene chemistry, and you can use these kinds of steps to make ever more complicated natural products. All right, questions so far? So how's this going to show up on your exam? But before I answer that question, which everybody's interested in, is there a hand back there? Did I see? No? Yes? No? Okay. How's this going to show up on an exam? Well, you can see clearly how I might do a mechanism question. One of the ways I like to do that is to show you a starting material, a product, and then mechanistic steps, and I say which of these mechanistic steps leads to that project, that product. For example, if we wanted to get, if the starting material were this geranyl pyrophosphate, and the product were alpha-thugene, I would show you these few steps that get you to this common intermediate, but then I might show you a couple of different steps, like this one that leads to alpha-pinene. It leads to something reasonable. It's a totally reasonable step, doesn't give you the right connectivity. Or I might show you this elimination step that leads to limonene. Again, totally reasonable, but doesn't lead to the right thing. That's one way to do it. Another way to do it is to put steps that are not reasonable, okay? To put steps that are not pi bond attacks an electrophile, or leaving group leaves from an allylic carbon, or elimination, or carbocation rearrangement, okay? So being able to follow mechanistic steps through, get the right connectivity, see how the pathway leads, to see how the mechanism steps lead to the correct product and are on the right pathway is important. A second way I can ask these questions is to simply give you a complicated natural product, as I said last time, and highlight the isoprene units for you, and then ask you, okay, which bonds were present in the linear precursor? So let's do one of those, and we'll do it with a sesquiterpene that has 3 isoprene units in it. So that sesquiterpene starting material is called farnesyl pyrophosphate. It's like geranyl pyrophosphate, only you've added an additional isoprene unit. And then here we go. Nope, that's not what we wanted. No, that was actually what we wanted. No, it still wasn't, sorry. This is called cedarol, a component of oil from the cedar tree, an essential oil from the cedar. Okay, so let's see how far you can get. I'm going to give you 2 or 3 minutes to try to identify the isoprene units in cedarol. See if you can do it on your own, or with a little help from your friends, but not from me. watching Clone Wars up here while you guys are working. Death Watch is working for Darth Maul. All right, you got anything yet? Or should I continue to watch the episode? Keep watching. What I don't get is why Bo-Katan was an enemy with her sister. I don't get that, but oh well. That's pretty deep in Star Wars lore. If you know who Bo-Katan Kryze is, you're a true Star Wars nerd. All right. So you got something you're willing to share? Anybody feel brave? Anybody want to use the Apple Pencil to highlight an isoprene unit? Don't be shy. So much power. Okay, let's do it. So feel free to use whatever colors you want.
Okay.
And oh, it's on the pen. Yep, switch to the highlighter.
This one.
Yeah, that's the highlighter. Good.
So we did this tail, and then and then here. You want me to do all of them, or?
So yeah, go for it.
Okay, so I did this, and then is that? I don't know if that's right. I think that's right.
All right,
I think
good.
I'm missing a way.
All right, so yeah, let's give him a hand. Bravery. Hey, keep the pen. Okay. So remind me your name.
Jacob.
Jacob. Jacob's very brave. Thank you. Tell me. So you're saying you're missing something. What are you noticing?
So this, I double counted this one.
Okay. So, and if you want to highlight things, you can use this is a laser. Oops. I don't know what I'm doing. So
I double counted this.
you double counted that one. You got that as 2 isoprene units. Okay. And you've also got a carbon there go ahead and highlight that one. Oh, sorry. There you go. That one hasn't been counted. So
Okay.
any revisions you can see that you could make to this to get it all to work. Pretty close. It's just a small one. Go ahead.
I don't know.
So let me use the laser pointer. What if instead of this one being, so this would be 1, 2, 3, 4, 5. What if instead of going up here to 5, you went here to 5?
Okay, and then, okay.
And then this one could be 5 from the green one.
Okay.
Yeah, go ahead and give it a try. The eraser, yeah, is right by the laser pointer, just to the left of the laser pointer. No, that one. Yep. So sometimes when you're doing this, you have to try something and it doesn't work, and then you're like, okay, how do I revise that? Often it's just a small change. The other thing you're going to notice about this is that there are sometimes alternative ways to do it. So Jacob chose a way where you sort of start with that dimethyl tail on the lower right-hand side, and you start moving around the molecule in sort of a clockwise way. There's probably some alternatives too. Okay, so now let's check that. You got 1, 2, 3, 4, 5, and then a bond between 5 of one precursor of one and the 1 of the other. 1, 2, 3, 4, 5. And then another bond with 1, 2, 3, 4, 5. Long as the methyl groups are in the right place and you've got bonds between 5 of one isoprene unit and 1 of another, you're good to go. Okay, very good. Thank you, Jacob. Okay, Any alternative pathways that you saw? Let's just, I'll erase here. And try to erase my notes. Whoops, I'm erasing bonds all over the place. Any other alternative ways of thinking about it? Go ahead.
I don't have an alternative way, but I was just wondering, so like, the new bonds are always between a 5 and a 1?
The bonds that we made, the bonds that are from the linear precursor, are always between 5 of one isoprene unit and 1 of another. So those are not the new bonds. Those are the ones that were there. Yeah, those are the original ones. Then the new bonds are everything else that's not, everything else between two different isoprene units that's not a 5 to 1 bond. Okay? Any other sort of ways of seeing isoprene units in this one? You have to choose this as the dimethyl tail. And these have to be, and these have to be carbons 2 and 3 respectively. The methyl groups are the guideposts. But what else might you do? I guess I could have gone up here. 1, 2, 3, 4, 5. No, I think that's probably, Jacob's way is the way. I'm not seeing anything else. Yeah, go ahead.
You could go up with the green and push the blue over.
Up with the green and push the blue over. Oh, yeah. Okay, thank you. So, you could still follow the relationship between green and red there, but instead you could go here for green and then 1, 2, 3, 4, 5. Yep. So you'll find that there are often reasonable, and in this case, these would be the bonds that are present, that were present in the linear precursor. So both of those are reasonable. I can't tell you which one is right versus which one's wrong. What I can do is show you a product like this, say these are the isoprene units. Now, which of the bonds are present, which of the bonds are old versus new? And to do that, the way the question would look is simply like this. I draw it like this, highlight the isoprene units, give you options A, B, C, D, E, and then you say which ones are new or which ones were present in the linear precursor. And as we've established, it's always the 5 to 1 bonds that are present in the linear precursor, and it's always the other weird bonds that are not. Okay? If you want to, as a challenge exercise, it might be fun for you to see if you can come up with a mechanism for this product formation from, I will redraw the molecule for you and get you started. From this intermediate, you get to the intermediate I'm about to draw via exactly the same steps that we used before in our synthesis of limonene. The only difference is this one's got a bit longer of a tail. But a question that we could ask is, can you get from there to there? And you're already well on your way once you've identified the new bonds you have to make, and numbering the carbons will help. It's going to seem kind of crazy and kind of bewildering. Oh, and the other thing I should do to help you out is the other thing I should do to help you out is just highlight the isoprene units here. Now, if you had chosen to draw this in a slightly different way, it's possible that your mechanism would need, if you had chosen to assign the isoprene units in the alternative way that we talked about, it's possible that you would need to draw a different mechanism, and that's fine. Anyway, it might be useful for you to see if you can get from here to here, or at least see how far you can get. I've got the mechanism in my notes, and I'll walk you through it, but that'll help you really sort of practice how to do this. Okay, so we have less time left than I wanted to, because all of this really comes together in the synthesis of a really complicated product that's a triterpene. That is, it has 6 isoprene units, and it's called cholesterol. So we're going to talk through this. Now, you're not going to have time to scribble all of this down. It's all in the notes. It's shown in your text, but it's shown in your text the way it occurs in nature, which is a lot of bonds form all at once. And that's kind of confusing. To help you understand it, I've separated out arrows step by step. I've highlighted isoprene units. We're going to go through it. But you'll see that each of these is one of our 4 basic terpene toolbox steps. So here's farnesyl pyrophosphate, 3 isoprene units. And there's a reaction that we didn't learn. It's a reaction that involves a reducing agent, which is called NADPH. It's like NADH, only it's got a phosphate group on it, an extra phosphate group on it. And this actually links 2 farnesyl pyrophosphates together, but not via a typical 5-to-1 linkage. This linkage is between green 5 of one farnesyl pyrophosphate and green 5 of another. So it's a head-to-head linkage. That's weird. It's not a typical step, and that's why it requires a reducing agent. People have studied that. You could learn more about it in biochemistry. If you really, really care about it, we could talk about it at office hours if you want. It's kind of crazy. But in the end, you get this molecule called squalene, which has 1, 2, 3, 4, 5, 6 isoprene units. Squalene is a lipid. It's excreted from your skin cells. It's part of skin oil, but your body uses it for other things in addition to that. If we redraw squalene to keep everything close to each other, I've highlighted gold, purple, green, red, blue, and pink isoprene units with the numbers. And again, notice that when we switch from green to red, we go to a 5-to-5 head-to-head linkage. So there's an enzyme called squalene monoxygenase that creates an epoxide with the pi bond between 2 and 4. Okay? You remember what an epoxide is from 351. You would have used MCPDA to do this in the lab, only look at all those pi bonds. This enzyme is able to position just the right pi bond in the right place. So you selectively make this squalene epoxide. Now, epoxides are electrophiles, right? They can be opened up because of ring strain, and they can especially be opened up if they're protonated. So, the enzyme protonates the squalene epoxide. Now, tell me what you know about epoxide opening. If the epoxide is protonated, which carbon gets attacked by a nucleophile? The more substituted one. If the epoxide is not protonated, the nucleophile attacks the less substituted side because the mechanism is more SM2-like, and so sterics matter more. If the epoxide is protonated, it gets opened up at the more substituted carbon because the mechanism leans a little bit towards SN1. The leaving group starts to leave even before the nucleophile comes in, and more substituted carbons better tolerate the positive charge. So that's what happens. The epoxide gets attacked on more substituted carbon 3. Now, the nucleophile happens to be the pi bond between purple 2 and 4, which is positioned in exactly the right place for this. And it's positioned so that if we make a new bond between purple 4 and gold 2, we have a positive charge on the more substituted carbon. So again, Markovnikov, regioselectivity, also selectivity for a more stable 6-membered ring. So that closes a 6-membered ring, but lo and behold, the cation on purple 2 is positioned very close to the pi bond between green 2 and 4. So immediately, and not even in a separate step, I've shown it here separately to keep it sensible and understandable. Immediately that pi bond attacks carbon-2. We form another 6-membered ring with another positive charge on the more substituted carbon. That's this intermediate. That forms 2 6-membered rings fused to each other. The orientation of the rings is trans. This methyl group on purple 3 is trans to the proton on purple 4. Again, you have a positive charge adjacent to a pi bond. Here we're going to see something unusual. Here we're going to see anti-Markovnikov selectivity. Here we're going to make a bond between red 2 and green 2 so that we can get a 6-membered ring. The positive charge will be on red 4. Presumably that carbocation is either stable enough to exist or it's not around long enough to matter. But forming the more stable 6-membered ring appears to be the driving force. And there's some notes here which I will post that explain what's going on. There's your third 6-membered ring, and at this stage you have a 4th pi bond that is close to that carbocation. We're going to close this up via Markovnikov selectivity to make the final 4-membered ring. That is the core steroid structure that all steroid hormones have, and it's established basically all in a cascade of carbon-carbon bond-forming reactions as nucleophiles attack electrophiles. Your text is going to show arrows pointing to arrows to indicate this happening. Now that's not it. That's not all. We are not done yet. Have you ever been driving on I-70 going into Denver and you think you're almost to Golden, but the sign on the road says, "Truckers, you are not down yet," because there's still nobody's ever been on I-70. Okay, whatever. We're not done yet. We're not done yet because we need a cascade of carbocation rearrangements that are going to take us from this carbocation all the way to this product, which is called linosterol. We're not even going to get to cholesterol because there's actually a sequence of 19 additional reactions to get from linosterol to cholesterol. But this is the common precursor to all steroids in the body, all hormones, all bile salts. We will finish that up next time and then move on to chapter 26, which is nucleic acids. Have a great weekend.